What are these square brackets doing in this function declaration? Or what about this type definition? And why are there tildes and bar characters in this interface? Hey, my name is Juani. My goal in this video is to get you to a place where you have a good understanding of how to use Go generics in your Go. Before we get started, if you want to follow along, make sure you have Go 1.18 or higher installed on your system. Okay, so the first thing that we want to do is to work on some generic functions. But before we do that, we need to create ourselves a Go project. So let's start with Go mod init, and I'm going to call this tutorial/generics. And we need to create ourselves a main file, and we're going to give it package name main, and we'll define ourselves a main function. Now we're ready to start coding. So I want to kick us off with a function that I've written many times in the past. And all that this function does is search through a list of values and tell us whether or not it can find a particular value that we're looking for. So I like to call this function has, and in this case we're going to take a list of strings, and we're going to of course be looking for a string value too. It will return a boolean, and what we're going to start with is we're going to range through our list, and if the value that we find is equal to the value that we're searching for, then we can return true, and if not, then we will return false. Now, if we jump back to the main function, we can test out our has function. So let's start by going format.printf, and we can pass in the string has a, and we'll provide a value, and don't forget the new line, and then we will say has and a list of strings, and we'll just say A and B in our list, and of course we're looking for value A because we're saying has A, but we'll do the same for value C as well. So we need to jump back into this string here, and we can change this to has C. Now what we should expect is that when we run this in the terminal, it'll say that has A is true but has C is false. And that's what we're getting. You might notice that the internal logic of the has function would actually be the same regardless of whether or not we're dealing with integers, strings, floating points, etc. Prior to Go 1.18, we had to commit the sin of copy-pasting this function every time we wanted to use a new type. Absolutely barbaric. But now with Go 1.18, we have a much better option. You guessed it, generics. A generic function has a type parameter list. This appears after the function name and before the function parameters in square brackets. We give each of the type parameters a name, often t, followed by a constraint. We can then define the input parameters and function as normal, but with the ability to use the parameterized types anywhere we like in our function. So we're finally at a point where we can convert has into a generic function. So let's start by jumping in and defining our type parameter list, starting with a type called t, and we're going to give it the constraint comparable. And what comparable does is it ensures that whatever value t is, it needs to implement the equality operator. Now let's change our list from type string to type t, and the same with the value that we're searching for. And there you have it. Has is now a generic function. Don't believe me? Well, we can now compile and run this, even though we're not specifying that has needs to take strings. And in fact, has will work for any type that implements comparable. So this would include things like strings, of course, integers, floating points, booleans, and a few other types. So let's show this by testing integers in main. If we copy paste the has function and we instead use integers as our inputs, we can say has list int 123, and we can change this value that we're searching for to say value 2. And finally we're going to print has 2. And if we run this, now you can see that has compiles for both strings and integers. You may be wondering why we didn't have to specify what type t was in our calls to the has function. How did the compiler know what types of values the has function was expecting to take? The compiler was using something called type inference to determine what type t should be in each function call. In each call, the compiler inferred that has was taking an integer or a string based on the inputs that we're passing into it. But determining t isn't always possible for the compiler. To demonstrate, we're going to write a function that returns an empty list for any type that we like. So let's start with func new empty list, and we're going to give it a type parameter list with t and the constraint any. And finally, it's going to return a list of t. Inside, all we're going to do is say return make t and 0. Okay, so now let's try and call this in the main function. So if we go format.printf and then pass in my list and go value new line, and then we can call new empty list, right? So here is a situation where our generic function cannot infer its type. So new empty list returns a list of t, but none of its input parameters explicitly say what t should be. So we get this compile error when we don't specify t, which says cannot infer t. However, if we do provide a parameter type, such as integer for example, then everything works fine. And in fact, we can compile and run this, and it will return our empty list. So basically, if the inputs to your function do not fully specify all types in your type parameter list, then you need to provide your types explicitly. Now before we move on from generic functions, I want to demonstrate how type parameter lists work with multiple type parameters. So let's start by defining a function print things, and it will take a type parameter list with capital A, capital B with constraint any, and capital C with constraint tilde int. The input arguments will be A1 and A2 of type capital A, B of type capital B, and C of type capital C. And internally we're just going to call format.printf, and we'll pass in a bunch of values into the formatting string, and finally pass in our input arguments A1, A2, B, and C. If we jump up to the main function, we can now call print things, and we'll just call it with 1, 2, 3, and 4. And if we jump into the terminal, we can go run, and it prints 1, 2, 3, 4. So no real surprises there. However, where things get a bit interesting is when we start changing the types of the individual arguments that we're putting into print things. So for example, A1 and A2 share the type capital A, so they need to be the same type. If we try and change one of them into a float, we get basically a compiler error saying, hey, the float 64 type does not match the inferred type integer. However, if we make them both the same type, then everything's fine, and we can compile and run this. Interestingly, capital B, even though it shares a constraint with capital A, is an independent type. So you don't need to match the type for B with types A1 and A2. In fact, B can be any other type it likes, like a string for example, and it's all good. C was just put there to demonstrate what happens when there's a different constraint, and it's nothing that interesting. C is just another independent type. Of course, C has the constraint int, so we can't do something, for example, like change this into a string, because a string does not have the underlying type int, so it does not meet that constraint of tilde int. Okay, so hopefully this clarified a little bit on how multiple parameter types work in a type parameter list. Generic functions gave us a feel for the power and usage of type parameters. There's only one other place that you're going to see type parameters, and that's in generic types. Generic types are defined as type, the type name, the type parameter list, followed by the type definition, which can now include types from our type parameter list. I know, I've said type a whole lot just now, but let's get into the code and we can write our own generic type. The generic type I want to write is called a set. Sets are types of collections that only hold unique values within them, unlike lists which can have duplicates. So how do we do this? We go type, set, and now our type parameter list, and we're going to use comparable for the constraint, and finally our definition will be map, t for the key, and we can use an empty struct for the values. And there you go, our first generic type. We're going to backpedal just for a moment and create another generic function. This function will create a new set for us and takes the type parameter of t with the constraint comparable. Its input argument is going to be values, which is a variadic of type t, and finally it returns a set of t for us. Internally we're going to say set is equal to make and then set of t, and the length can be the length of the values that we're passing in, and then for each value in the range of values we're going to say set v is equal to an empty struct. So that sets all the values in our set for us, and finally we can return that set. So there you go, generic function to create our generic type. Generic types get a whole lot more useful when you start defining methods for them. So let's do that now. I'm going to define a func and s as our receiver of type set of t, and we can call this method has, and it's going to take a value of type t and return a boolean. Internally we're going to say OK is equal to s of value, and we can actually just return the comma OK value here, and that determines whether or not our set actually holds the value that we're looking for. So how about we go and jump into the main function and try this out. I want to start with int set, which will be a set of integers, so we'll say new set here and say 1, 2, 3, and then we can start testing this int set by going format.printf, and we'll pass in our formatting string of, say, has 2 and then the value, and then we can go int set dot has and pass the value 2 in. And for completeness, let's also pass 5 in here, and why not build and run in the terminal. There you go, has 2 is true, has 5 is false. If we jump back into the code, we might also want to see if this will work for strings. So if we go string set is equal to new set, and we input the values a and b, then we can also once again test with format.printf, and this time we'll say has a with the value, and we can call string set.has and check for the value a. Once again, going back to the terminal, we can run this, and this also works. So there you go, that's how you use methods with your generic types. We now know how to generalize functions and types using the type parameter list. But how can we restrict what our generic functions and types will accept? This is the job of constraints. Constraints are kind of a double-edged sword. On one hand, they restrict what types we can use, but the more restrictive a constraint is, the more we can usually do with the type that we do accept. Constraints introduce some strange new symbols, such as the tilde for denoting an underlying type, or the bar for denoting a type union. To keep it simple, we'll go through each of these concepts one at a time. So the first constraint that we're going to look at is the any constraint. The any constraint accepts any type that we pass to it. Sounds great, right? Well, unfortunately, because it accepts anything, we really can't do much with the value that we pass, because we have no idea what it is. Allow me to demonstrate in the code. So firstly, we're going to format.printf in the main function, and we're going to pass a formatting string has to value v, and then the next thing is to pass in a value of a call to a function has, which we've defined in the past, but we're going to do it again soon. And it's going to take a list of integers, in this case, of 1 and 2, and the value that we're searching for will be 2. And now we can define our has function. So we're going to go function has, pass in a type parameter t, but this time the constraint is going to be the any constraint. And next it's going to take an input parameter list of type t and an input value also of type t, and of course return a boolean. And inside, what we'll start with is by returning false if we don't find anything, but otherwise we're going to range over our list, and if the value that we found is equal to the value that we're looking for, of course we return true because we found our value. Okay, so this is looking very similar to what we've written before, but you'll notice that there's a red squiggly line on this V. What's that about? Well, it says here the type parameter t is not comparable with equals equals. So basically, because our constraint is any, we don't actually know that it implements the equality operator. So this is a no-go for us using this v is equal to value operator here. Now, how would you fix this? Well, normally you'd use a different type constraint, right? Probably the one that we've seen before called comparable. But in this particular case, if we want to force the any constraint to work, there is another way. So what we're going to do is define an input function, and this function will be called equal. So we go equal func input a and b of type t, and it's going to return a boolean. And we can call this equal func down here by going if equal v and value, then we're going to return true. So great. Now our has function will compile, and all that's left to do is to make our call to has work as well. So back up in the main function, we can define an equal int function like so, which is going to take parameters a and b of type integer, in this particular case, return a boolean, and all we're going to do here is return a is equal to b. And finally, we can pass this equal int function into our call to has, and there we go. We've now forced our any constraint to still work with our function has, so that we can look through a list of values and see if it contains the value that we're looking for. So just to demonstrate, we can compile and run this, and it works. But hopefully it demonstrates to you how limited the any constraint actually is. The next constraint that we're going to look at is called comparable. We've seen comparable before, and what it does is accept any types that implements the equality operators. To be specific, the equality operators are the equals equals operator and the not equals operator. Let's demonstrate this in the code. So we're going to update our has function to use comparable. And what this is going to do is help us tidy up our has function quite a lot, because we can get rid of this call to our input function equal and replace it with just a v is equal to value check. Next, what we can do is remove our input function equal, because we don't need it anymore, and do the same up in our main function. There we go. And as you'd expect, this compiles and runs. So the comparable constraint works with a bunch of different types: floats, integers, strings, booleans, and any structs that are only composed of other comparable types, as well as a few others. The next constraint I want us to take a look at is the interface. Go interfaces can be used directly as constraints into our type parameter lists. Allow me to demonstrate in code. We're going to start by going type and then equalizer as our interface, and it's going to have a single method called equal, and equal is going to take an input of other and return a boolean. Now we're going to hit a little bit of a snag here because we don't know exactly what type other is, so we're just going to specify this as a t, and in fact turn equalizer itself into a generic type, where t can be anything. This is kind of okay because we don't really care what type t is, so long as whatever's calling equal can actually check that the other type equals it. So down in our has function, we're going to replace comparable with our equalizer interface, and we're going to actually pass the same type t into equalizer, because we want to check like for like types here. The next thing to do is in our if statement, we can replace this equality check with a value dot equal, and of course pass in the value that we have found. And now has takes a go interface as its constraint. Let's jump up and actually define the type that implements equalizer. So we can say type, and in this case I'll call it ID, which is just an integer, and we can give it a method. So we'll go func receiver ID, and the method name is equal, and other ID. We're going to return a boolean here, and all we need to do here is return ID is equal to other. So now that we have a type that actually implements equalizer, we can demonstrate it in our main function. So in our call to has, we're going to replace int with ID, and there you go. Because ID implements the equalizer interface, we have no more compile errors. And of course, as you'd expect, we can build and run this, and it works. So there's an example of using Go interfaces as our constraints. Generics have introduced a new symbol to Go, the tilde symbol. And the tilde symbol is used in a specific type of constraints. And this type is called the underlying type. So for example, if we had a type constraint of just string, then the only thing that that constraint would accept is strings. However, if we had a type constraint of tilde string, the types that would accept are strings, or also anything with the underlying type of strings. So what does this mean? Well, allow me to demonstrate in the code. The first thing we're going to do is go to our has function and change equalizer to be int. Down in our if statement, we're going to get rid of this value equal and change that to v is equal to value. And now our has function has a constraint of just int. So back up in main, we need to change this list from an ID list to an int list, and everything compiles. The only weird thing about this is why would we have a type parameter list if it's only ever going to accept one type? So if we add a tilde in front of this integer constraint instead, now our has function will accept anything with the underlying type of int as well as int. I'm just going to tidy up this equalizer interface now because we don't need it anymore. But one option for an underlying type of int is actually that ID type that we've already defined before, because ID happens to be of underlying type int. So we can call has this way and we have no compile errors. However, if we change the underlying type of ID to something else, like say a unsigned int, then again we're going to get compile errors because ID does not implement tilde int. So to summarize, if you want your constraints to allow underlying types in your generic parameter lists, make sure you use the tilde symbol. The bar symbol has a special meaning in type constraints, the union. Say we have int bar string. What this means is that our constraint will accept anything that's an int or a string. Unions are, however, exclusionary in terms of what implementations we can use our type parameter for. Let's go to the code and see how this might work. Say we want a function called compare, and it has a type parameter t of type int bar bool. And we're going to have two input arguments, a, b of type t, and we want to return an integer. Now how I want this function to work is that if a is equal to b, then we should return 0. If a is less than b, then we should return -1. And finally, we're just going to return 1 in all other cases. So the first case, if a is equal to b, then we can return 0. So far, so good. But if a is less than b, when we return -1, we can see that we've hit a little bit of a snag here. We have this red squiggly line under a, and it says here that we can't compare a as less than b. So what's going on here? Well, in the case of our integer in our union, integers certainly implement the less than operator, but the other type in our union, bool, does not implement the less than operator. So, because unions are exclusionary over what implementations you can use, we cannot use the less than operator in our function logic. So to summarize, when it comes to unions, all types in the union can be used, but only the shared implementations can be used in your function or method logic. So far, we've learned about all the different types of constraints: any, comparable, interfaces, underlying types, and type sets using unions. But surely there's a way where we can combine some of these constraints. Well, yes there is, and we can do this using interfaces. Let me show you in the code. So I'm going to define this currency interface, and we're going to start off with a tilde int bar tilde int 64 as our first constraint. So this will accept anything with the underlying types of int or int 64. And we're also going to define an ISO 4127 code. And for those who don't know, that's kind of any currency code like the USD for the US dollar, for example, which means that this should return a string. And then the last thing we're going to do is also require that currency provides a decimal function of type int. Now, I'd like to use this new set of constraints in a generic function. So I'll define print balance, and this will take type t of constraint currency, and it'll take a single input b of t. the balance that we're going to print. And the next thing to do is to convert balance into a floating point value. And I also want to adjust the decimal points of our floating point value, so I'll divide it by math.pow10, and inside here we can pass in the balanced decimal points. And finally we can print this value, so we'll go format printf, and we'll pass in our formatting string, which will be a dot because we want to print decimals to a specific number, which will be provided by this asterisk, and it's a floating point type. And we're also going to print the ISO 4127 code with the %s. So here we go b.decimal as our first argument, balance as our second argument, and then finally b.ISO 4127 code. Great, so now we have a function that wants to use our combined constraints. The next thing to do is to define a type which actually meets all of these constraints that we've defined. So I'm from New Zealand, so I'm going to use the New Zealand dollar as the currency that I use. But feel free to use whatever currency you want. So we're going to go type NZD, and in this case I'm going to make it an int64. And so now we've met the first constraint, but we need to meet the other two. So let's make the New Zealand dollar a receiver of a method ISO 4127 code. And in here we can just return NZD. And then finally we'll make another method called decimal. And this will return an int, and we can return 2 here because the New Zealand dollar has 2 decimal places. So to test out this new generic print balance function, let's call it up in main. We'll go print balance, and we'll pass in NZD 250. And everything's looking good, so why not compile it and run it in the terminal. What I would expect here is to see $2.50. Great. So in this example, hopefully this has demonstrated that combining constraints in our interface gives us really fine-tuned control over exactly what we can do with the types that we pass into our generic functions or methods. And we're done. I hope that you're excited to start writing generics in your code. If you'd like to learn more, I recommend reading through the spec. Links in the description. See you later.